in the Monroe group, where we've been performing quantum simulations of various spin models using linear chains of trapped ions. Now, in general, in the quantum simulation game, what we have, or what we try to do, is take some complicated many-body system, which may be difficult to describe numerically or analytically, and we take that system and we map it onto another well-controlled quantum system, and using that well-controlled quantum system, trapped ions for us, we'll be able to investigate the properties of this difficult-to-understand system. And that becomes really important, especially as the number of interacting spins in your system approaches about 30 or beyond, because that's really the threshold over which it's very difficult to perform classical computations. And in particular, if you're interested in dynamics or what happens in excited states of these sorts of systems and maybe how they thermalize or other sorts of dynamical properties, it becomes very difficult to describe classically what goes on. So instead, we map that over to our well-controlled quantum system, and we can do all of those type experiments in the lab to investigate the behavior of these systems. Okay, so all that work is placed into the context of our group doing these sorts of experiments for several years now, starting with small systems where we can map out the ground state phase diagrams, look at the onset of quantum phase transitions as we increase the number of spins in our system from 2 to 9, and also probe some elementary studies of frustration, which were later improved upon, and I'll talk about those a little bit here. The main focus of this talk are a few of our more recent results. One, I'll say a little about how we can optimize adiabatic evolution in our system to better prepare ground states of our system. And then I'll focus on two of our bigger results. One where we can introduce controlled quantum fluctuations to study a classical model at 0 temperature. And another where we're actually for the first time performing a spectroscopy on our effective many-body Hamiltonian that we're engineering entirely. And we can use this as a way to sort of verify and validate that the quantum simulations that we're performing with the Hamiltonians we think we're applying are actually the Hamiltonians that the ions are seeing in our simulations. And then in the end, I'll wrap up just a little bit with some of the future work. All of this is going towards this idea of scaling up the number of interacting spins and starting to study these kind of dynamical processes in our systems. So it's a really large overarching theme of the talk that we're moving from studies of static and ground states to excited and dynamical type states in our simulators. Okay, so all of our experiments take place in this 3-layer Paul trap that's housed in this vacuum chamber here with background pressure of about 10 to the minus 11 torr or so. Into the trap, we load ytterbium-171 ions. We arrange the voltages so that they form this linear chain here. And we can image these directly on a CCD camera. If you zoom in on any one of these ytterbium ions, way down in the ground state, we have this hyperfine splitting. We call the down state the 0 state. The up state is this 1 state, and they're split by about 12.6 gigahertz. This qubit is magnetic field insensitive to first order, and so we get excellent coherence times of greater than a second without any fancy magnetic shielding or anything like that. When it comes time to figure out exactly what spin state the ion is in, we can apply a spin-dependent fluorescence technique. We shine in 370 nanometer laser light, and if the ion is in the up state, then it will scatter many photons, which we can then collect on our CCD. Whereas if the ion is in the down state, then this 370 nanometer light is no longer resonant with any transitions, and we don't collect any images or photons scattered onto the camera. Now, in order to generate the kinds of spin-spin couplings or spin-spin interactions that we want to engineer in these many-body systems, we need a way to perform some sort of entangling gates, and there are, of course, a large variety of proposals and methods to do this. Ours most closely follows the Molmer-Sorensen type interaction. We start with a linear chain of trapped ions, and then we address them with 2 laser beams, one at frequency omega, the other at frequency omega, plus the hyperfine splitting, plus and minus a detuning mu. Now, when that detuning mu is set equal to 0, this is just a Raman transition where we can drive population from spin down to spin up while coupling through this virtually excited state here. And we do that at a carrier frequency, which is just the hyperfine splitting. Of course, all of these ions live in an ion trap, and so we have all of these secular frequencies, these axial modes, and also the transverse modes that are to the red and to the blue of these this carrier transition. And if we set these 2 detuning frequencies, so the 2 colors in this beam, at plus and minus mu, so they're symmetrically detuned from the carrier, we can get them to couple most strongly to these transverse modes. And then it's well known that when you do this, then you can generate an effective spin-spin Hamiltonian with the spin-spin coupling terms given by this Jij matrix, Jij in particular depends on things like the Rabi frequencies at each of the ions, the normal mode eigenspectrum, as well as the individual frequencies of all of these modes that it's coupling to. And in general, when you go through it, these Jij coupling terms fall off with a power law in the distance between the ions, and that'll be important later for what we're describing. Now, all this works when you are cooled down into the Lamb-Dickey regime, and so as a little bit of an aside, I thought I might just show that the mass of a terbium is rather large, so our Lamb-Dickey parameter eta is about 0.06. We sideband cool down to about n bar of 0.05 to 0.1, and so we're well within the Lamb-Dickey regime here. You might wonder a little bit about motional heating and whether or not that affects our gates, but we measure in our trap an n bar dot of about 20 quanta per second or so, and given the times that our simulations last, which is of order of a few milliseconds, the change in fidelity on these types of Moll-Morsorans gates is about a part in 10 to the minus 4. So we're not really so concerned about heating in this experiment. Chris, I think in the topical group discussion, will talk about 2 other experiments in the lab where heating is not at all an issue just by design. So stay tuned for that in a few days. Okay, so that was the aside. We can generate the spin-spin interaction and make this Ising-type Hamiltonian. We can also add a transverse field to this Ising Hamiltonian. It's transverse because we have a sigma y magnetic field here, which is perpendicular to these sigma x terms. We do this just by adding another color to this laser beam here, just at omega plus the hyperfine frequency, and it's just a carrier transition that can flop us from spin down to spin up. Okay, well, when performing an experimental protocol on this Hamiltonian, we typically go through 3 steps. First, we initialize all of our spins to point along the y direction, and we do so that when we turn on the Hamiltonian with by much, much larger than j, we will have initialized ourselves into the ground state. We then adiabatically lower the by field, leaving just the jx, the spin-spin coupling term at the end, and then finally we can measure all of the spins along the x direction. And if we've really ramped this down adiabatically, then what we expect is for an antiferromagnetic Hamiltonian, we'll get a spin ordering that we can measure out that is the staggered order, a spin up, down type ordering. Okay, so to give you a feeling of how these experiments might go, we can start with this Hamiltonian, and then we can measure what the correlation function is across the chain in the x direction as a function of what b over j is, or where we are in the simulation. So initially, when b over j is very large, all of the spins are polarized along the y direction, and so there is essentially no correlation along x. Now as we decrease b over j just by a little bit, we can see a little correlation popping up here, maybe between the first and second and third ions, but really not so much. But as we continue to lower b over j, then we can see clearly the staggered up, down order come out, and that's a signature of us making this antiferromagnetic ground state. Now, I'd mentioned earlier that the spin-spin couplings fall off roughly as a power law in distance between the ions, and that's parameterized by some number alpha. Now, a large alpha would be a short range, and a small alpha would be a long range type interaction, and that's actually a knob that we have control over in our experiments to tune. The way we do that is actually by changing the axial frequency, which will essentially expand or compress the bandwidth of all of the transverse modes. And in our experiments, we can, roughly in the axial frequencies that we can stably trap our ions, we can engineer alphas of between 0.5 and about 1.5. And now one of the immediate consequences of tuning the interaction range here is that we can make the system more and more frustrated. So if you consider just having nearest neighbor interactions, if you have an antiferromagnetic Hamiltonian, this spin can be down, then this can be up, and this can be down, and all of the bonds are satisfied. But as soon as you go to a next nearest neighbor interaction, then it's no longer possible to make these spins anti-aligned, these two anti-aligned, as well as these two anti-aligned. So you've now introduced frustration into the system, and you can see as you go to longer and longer and longer range interactions, you're going to be introducing more and more frustration into the system. One of the consequences of moving to longer and longer and longer range interactions is that the energy gap between the ground state and the first excited state will get smaller. It becomes easier to make excitations when there's more frustration into the system, and so the energy gap between the ground state and the first excited state shrinks for long range interactions. And so if we were to do an experiment to probe the increasing amount of frustration in the system at long-range interactions, what we can do is we can ramp the Hamiltonian non-adiabatically, but at the same speed as we change the range of interactions, and use that as a probe of frustration. So here's what we did. Here I'm plotting the structure function, which is the Fourier transform of the correlation functions I was discussing earlier. And we'd expect a peak in the structure function at a wave vector of 0.5, which is equivalent to a lattice spacing of 2. So we'd expect a peak due to the fact that every other spin is aligned with its next nearest neighbor. For short-range interactions, we have a peak, but as we move to longer and longer range interactions, that peak is getting suppressed. And that's a signature of the fact that we're making more and more excitations in the system, exactly as we might expect. Since we have a camera and we're imaging all of the individual spin states that we're making, we can clearly tell the difference between all of the spins in the state up, where you have all this fluorescence, and all of the spins in the state down. There really is data here. And if we're making all of the antiferromagnetic ground states, they look something like this. So we have two degenerate ground states, up, down, up, down, up, down, or down, up, down, up, down, up. Now, when we perform an experiment where I do what I've told you before, we do it about 2,600 times, we find about 440 times or so we're making these ground states, or about 17%. That's not 100% of the time because we're not ramping the Hamiltonian adiabatically, but it's still much larger than the percentage that you would expect from random chance on its own. We can also map out the first excited states in our system that we're going to be making when we don't ramp adiabatically, and these are the signature of these is that you have domain walls. You have two spins down or two spins next to each other, up next to each other, and that costs energy in an antiferromagnetic Hamiltonian. And since we have a camera, we can in fact map out the distribution of all possible 2 to the 10 in our 10-ion system, 1,024 states. Initially, when B is much, much larger than J, we have a roughly uniform probability of making any state, save for a few detection errors here and there. Whereas once we've ramped down to B equals 0, we can see that these two nominal antiferromagnetic states are really popping out from all of the background. So we're making these with much higher probability compared to any other state in our system. Now, in fact, you can show that the most prevalent states, when you plot a distribution like this, should always be the ground state. And in fact, we've taken this idea and extended this up to 14-ion system, where for these 14 ions, you can again see these two antiferromagnetic states. They only have a state probability combined of about 3%, but still it's very easy to pick them out compared to the probability of making any of the other 16,000 or so possible states in this 14-ion system. Okay, now even making that 3% in the ground state for the 14-ion system required a little bit extra optimization of our ramp protocols. So far I've only been talking about exponential type ramps where we decrease this transverse field exponentially. But you can imagine decreasing it in different ways. You can decrease it linearly, that has a profile like this, or you can decrease it in a way that I'm going to call locally adiabatic, which kind of has this funny shape that goes down quickly at first and then really smooths out. And to understand where that shape comes from, we have to make reference to the energy spectrum of our system. And so typically, when we have an energy level diagram versus the value of the transverse field, we have a ground state here in red and a first coupled excited state that looks like this. And there's a critical gap at some critical transverse field. Now, in such a system, we can define an adiabaticity parameter. This comes just from the adiabatic theorem, and that's the ratio of the square of the instantaneous gap at any B field divided by the rate at which we're sweeping the B field. And just like your intuition might say, if the gap is very large, then you can be very adiabatic. And similarly, if you're ramping very quickly, then you're not going to be so adiabatic. And what a locally adiabatic ramp tries to do is keep this adiabaticity parameter fixed throughout the entire evolution. And so one of the consequences is that right around this gap, when this gap is very small, B dot also has to be very small to conserve the adiabaticity throughout. Okay, so here I'm plotting just theoretical curves of what the slope of linear exponential or locally adiabatic ramps is as a function of this transverse field. And right at the critical point, you can see that locally adiabatic ramps have the smallest slope. That's by design. And as a result, if you look at the diabaticity, or 1 over this parameter, linear and exponential ramps are very peaked around the critical point, and so you'll be making lots of excitations, whereas locally adiabatic ramps are flat throughout the entire evolution, again, by design. So when we actually turn these sorts of profiles onto our ion chain, we can actually see a vast improvement over a factor of 2 for exponential ramps or a factor of 4 compared with linear ramps. Just by taking this locally adiabatic ramp profile, we can get something close to 80% in the ground state for our 6-ion system. And it's a frustrated 6-ion system. Okay, so that's by way of introduction. So far, we've been talking about a Hamiltonian that has a spin-spin coupling and a transverse field. I've showed you that we can vary the range of interaction of the spin-spin coupling, and we can find increased frustrations as we've moved to longer range interactions. Also, I've just told you that we can vary the ramp profile of our transverse field, and we can put more population into the ground state when we use a locally adiabatic ramp. Now I'd like to switch a little bit to a similar looking Hamiltonian, but qualitatively different in a number of ways. Here I take this transverse field with a sigma y, and I replace it instead with a longitudinal field, sigma x. So the magnetic field here is just in the spin-spin coupling direction, and this is an entirely classical Hamiltonian. And in this classical Hamiltonian, we're going to study the effect of varying the strength of this longitudinal field. And what you can calculate is that when you do so, you'll go through n over 2 classical phase transitions as you increase the strength of Bx, where n is the number of ions that you have in your system. Okay, so if we have this Hamiltonian, then we can again make an energy level type spectrum of it. And it looks something like this. You'll notice that in this 6-ion system, we have 3 distinct points where the energy level goes through these kinks here. And these are the locations of first-order phase transitions. If we zoom in and see what the ground state energy eigenvectors look like, or the energy eigenstates, near Bx equals 0, we have this antiferromagnetic up-down, up-down, or down-up state, as you might expect near B equals 0. Now, as you continue to increase the strength of Bx here, it becomes at some point energetically favorable to flip one spin polarized along that external field. And so our new ground energy eigenstate looks something like this. We have another spin flipped down. As we continue to increase the external field, another spin flips down until at very large field, all of the spins are polarized to point along this external Bx field.
So Phil, I have a dumb question. You said it's classical. It looks kind of quantum to me. Why do you say it's classical?
I say it's classical because all of these are sigma x operators, and so everything commutes with each other. And if you look very closely on any of these energy level diagrams, you get all of these are level crossings rather than avoided crossings. So that's why I say it's a classical system. Now, in this system, if we plot some order parameter like the number of ions bright as a function of this transverse field, of this longitudinal field, then we get a staircase-like structure. And one of the interesting things here is that these steps are only present for antiferromagnetic Ising models when you have long-range interactions. So if you have only nearest neighbor interactions, you actually have a massive degeneracy, and all of those steps start to line up on top of each other. And it's these long-range interactions that break the degeneracy and allow you to actually see the entire staircase. Okay, so if we want to go study this in the lab, we have effectively a zero-temperature system since our qubit coherence time is so good. But we run into a problem. And in fact, it's a general problem whenever you want to study a classical system at zero temperature. And I'll illustrate it like this. So consider we can start by making one of these states that's really polarized all along at a large B field. And then if we want to make one of these other ground state spin phases over here, you might imagine that we can start at large B field and then start ramping it down. Now, when we reach the phase transition, we should go through that phase transition and land in a new ground state. But at t equals 0, there's a lack of thermal fluctuations that would drive that phase transition. And so as a result, we won't transition to a new ground state, and instead the system will remain in the same phase. It'll just follow this energy level all the way up. We'll hit the second phase transition, or what should be the second phase transition, and the same thing will happen again and again. And throughout the entire evolution, we would stay in just this initial polarized state like we started due to the lack of thermal fluctuations. Instead, to get around this, what we do is we add quantum fluctuations to drive these phase transitions. They're just as good as thermal fluctuations, and then that'll allow us to create all of these ground state spin orderings that we couldn't classically create otherwise. Okay, so here our experimental protocol takes this longitudinal field Ising model, and it adds this transverse field part. This adds the quantum fluctuations because these sigma y's now no longer commute with any of these sigma x's. So here our protocol is similar to before. We initialize all of the spins along the total B field direction, Bx plus By, so that again, when we turn on our Hamiltonian, we are again initialized into the ground state. As before, we slowly lower the transverse field, and at the end, we measure the spin ordering along the x direction. So I've showed you before that we expect this sort of staircase structure for the number of ions bright versus Bx. When we actually go and take the data points look something like this. So they start in the correct place, they end at the correct place, but really the staircase structure is getting washed out. And the reason there is just simply because we're not being adiabatic enough with our with our ramp of our transverse field. And so in blue here is kind of a numerical simulation of what we might expect, so things are making sense at least from that point of view. However, we can use this idea from before that the ground state at any point is really just the most prevalent state when you look at the entire energy distribution, look at the entire probability distribution. And so what we can do is that at each point we can go in and pick the most prevalent state and look at the number of ions bright in that state. And when we do that, we recover these black points, which again show the staircase structure as you might expect. And we can locate the positions of all of these phase transitions with error bars in gray here. And you see that all of them line up very well. So this is not something that you can do classically. We had to introduce quantum fluctuations to get a curve like this. In addition, since we had a camera, we can map out exactly what are the spin eigenstates that we're making at each of these plateaus. And in fact, we find the antiferromagnetic ground state when we're at Bx near 0. And then we transition to 2 bright, 1 bright, and 0 bright ground states. So this is all making sense, and this is all agreeing with the classical calculation of what should be happening here. We can also extend the system out to 10 ions, where of course the data gets a lot noisier, but nonetheless, using the camera, we can see that we're making these 5, 4, 3, 2, 1, and 0 bright ground states as well. Now, I'll also point out that there's a lot of interesting spin ordering that starts to happen here when you get to higher numbers of ions. For instance, moving from the 5 bright to the 4 bright ground state, it's not as simple as just taking one of these bright ions and flipping them dark. There's really a rearrangement of which spins are bright here. It's actually solving the energy optimization problem, putting Q spins on n lattice sites and doing so in a minimum energy configuration. It's really like making a Wigner crystal of spins here. Now, as the system size here, n goes to infinity, this staircase structure turns into a fractal Devil staircase, and that arises due to the fact that that every rational filling factor has its chance to be the ground state at some point, and there are an infinitely large number of rational filling factors. Now, to really hammer home this idea that it's the quantum fluctuations that are driving the phase transition, we can look at the ramps that we're doing of this Hamiltonian here in the phase diagram of By versus Bx. So in the experiments I've told you about, we're ramping picking a particular value of Bx, we're ramping down By. We're at t equals 0, so there are no thermal fluctuations, but we're introducing quantum fluctuations. And here we can plot the probability of being in any one of these 4 ground states. So at low Bx, we're in this blue ground state, the AFM ground state, and then we transition to the green ground state, the red, and then the black at the end. And we can locate where these phase transitions are occurring. If we instead did not use quantum fluctuations in the system, if we just had sigma x here, and then just this longitudinal field, and instead we ramped down, we've also done that experiment, what we find is that we start in this all polarized state, and that state remains dominant throughout the entire revolution. We're hardly ever making, if any, population at all in any of these other ground states, and certainly we're completely blind to where those phase transition locations should be. And so this really highlights that we need quantum fluctuations to study these sorts of zero temperature systems. Okay, now the second big experiment that I want to talk about all stems from this idea that we're moving from ground state type systems and the statics of all of these sorts of interacting spin systems to their dynamics. And we'd like to begin studying the excited states in particular because it's difficult or maybe even impossible to figure out what's going on dynamically if you try and involve a Schrodinger equation that's described by a 2 to the 30 by a 2 to the 30 type matrix. I also think that excited states are rather interesting. Now, one of the experiments that I'll talk about immediately is spectroscopy of this sort of many-body Hamiltonian. By the way, all of this spaghetti out here only comes from exact diagonalization of a 6-spin system. And so you can imagine how rich that structure really gets when you start getting up to 20 or 30 spins. But also excited states will lead us into studies of non-equilibrium phase transition, how quantum systems thermalize, and really get at a lot of the open questions in quantum systems right now. But for Hamiltonian spectroscopy, we want to take a look at a system like this, and we really want to verify that the Hamiltonian that the ions are seeing is the one that we think that we're applying to the ions. And our method for performing spectroscopy is to take this Bayer-Ising Hamiltonian and apply to it a transverse field that we modulate the amplitude with some frequency omega. And the key here is that this modulation is a small perturbation to this Bayer-Ising Hamiltonian. And when you have that, then we find that we can drive transitions if 2 conditions are met. And both of these will be very familiar just from ordinary atomic spectroscopy. The first condition is just that there's a non-zero matrix element that couples the 2 states via this sigma y here. And the second is that this drive modulation frequency has to match the energy splitting between the two states that we're looking to couple. And if those two are met, then we find that we can drive transitions from one state to another. So in our experiment, first, we have to initialize. So we can initialize either in the ferromagnetic or antiferromagnetic state of this Hamiltonian. So that'll be the ferromagnetic state all the way up here, or the AFM state way down here. Next, we turn on this sort of perturbation, this driving field, for about 3 milliseconds. And the states that we can possibly couple to are the ones with the non-zero matrix element. And so that's these 6 states here in color. And then finally, we can scan omega, this perturbation frequency. We can scan omega and see where we find those resonances. And that'll exactly map out what those energy level splittings are. Okay, so our experiments are performed down centered around By equals 0. And if we wanted to start from this antiferromagnetic ground state, we can drive to any one of these 6 states. They all differ from this antiferromagnetic ground state by exactly 1 spin flip. And you can see that here because those are the only states for which you have a non-zero matrix element with a single sigma y operator. So when we start from these states, we can plot the probability of remaining in the AFM ground state as we scan our probe energy or our probe frequency. And we find that there are, in fact, 3 distinct resonances as we're depopulating the ground state. Where's the population going? It's going into these 6 states here. So in blue, this is at this lowest energy level, these 2 symmetric states, and then also we have these other 2 resonances that we can trace out. So just with one modulation frequency starting from this antiferromagnetic ground state, we can map out these 3 energy levels and find exactly what their splittings are. Similarly, we can also start from the ferromagnetic state where we're polarized all in the up direction. We can couple to these 6 states, and likewise, we can trace out these resonances all very nicely. There's no reason to stop at 6 ions. We've extended this up to 12 in our system, where here there's a left-right symmetry, as you might have noticed, and so we have essentially 6 different excitation energies that we're mapping out. One of the very interesting things is that if you look at the energy cost of just taking this spin at the left end of this 12-ion chain and flipping it from up to down, you can calculate that the energy cost of doing this is 2 times J12 plus J13 all the way out to J112, where again, these Jijs are the Ising coupling the coupling matrix for all of the Ising interactions, which I'll remind you has this form from before. And the things that I want to highlight here are that this Jij matrix depends on the Rabi frequency of the at the ions and these normal mode frequencies. And I'm highlighting these things because as experimentalists, these are the things that tend to drift in our experiments or from experiment to experiment. You can have laser intensity noise, or you can have a transverse mode frequency that might be shaking around a little bit. And so just by measuring what this energy level splitting is, just by looking at where this resonance lies, that can actually be a good proxy for what the entire Hamiltonian is doing. And so we can measure this, and we've actually used this in our experiments to see when our trap has come into equilibrium after we may have lowered an RF voltage, or maybe after we've loaded ions. We wait for a resonance like this to reach an equilibrium value, and then we know that our Hamiltonian is in equilibrium, and we can continue on with our experiments. Okay, so everything that I've told you so far is applying a single perturbation, and we can drive any of these single spin flip states, but there's no reason to stop there. We can use a single perturbation to go from some ground state to an excited state with 1 spin flip, and then we can use that as a launching off point to then make a 2 spin flip state. And of course, we can then use one of those to launch off and make a 3 spin flip state. And so just starting here, we can make this array of states. Starting from the other polarized FM state, we can now add these states to the mix, and likewise, if we start from the antiferromagnetic states way down here, then we can kind of fill in the table of all possible states that we can be making in this 5-ion system. And so measuring frequency splitting after frequency splitting after frequency splitting, we can actually assemble what the entire energy eigenspectrum that the ion sees in our system is for this 2 to the 5 or 32 energy level system. And we can compare what the ion sees to this calculated energy spectrum, which we get just by giving it an Ising model with a small axial field, just to break a few of these degeneracies here. And so we can really see for the first time what the ion Hamiltonian is by directly measuring it, and I think we get great agreement here compared to what we think we're applying on the ion. I think this is the first time that such verification has been done in a quantum simulator. Okay, now you'll notice before we did that in a 5-ion system because there's 2 to the 5th energy levels in a 5-ion system. As you move to larger and larger systems, measuring 2 to the n energy levels becomes intractable even from a measurement point of view. But instead, measuring the spin-spin coupling, the values of the spin-spin coupling here can be done in a scalable way for 2 reasons. First is that J is an n by n matrix, and in general there are of order n terms in that matrix. And second is that a single frequency scan for us will go from, let's say, an all-down state to all possible one spin-up states. So a single frequency scan gives us of order n energy splittings. And so for us, if we do n frequency scans that give us of order n frequency splittings, then we can recover the n squared Jij terms in our matrix. And so we've done this for our 5-ion system, measuring the couplings directly. We find excellent agreement with what we might predict again from the theory and the equation for Jij that I've showed you earlier. And this is something that we're looking in the very, very near future to extend up to 10 or 12 or 14 ions and measure those couplings.
Can you do like a off-resonant Raman transition, like sort of many-body Raman transition?
I see. To go from a 0 spin flip to a 2 spin flip, for instance?
Yeah, via some virtually populated.
It might be possible, but I think, again, to make an atomic physics analogy, it all has to, you have to be careful about the power when you're doing any of these kinds of off-resonant transitions. And I'd say in our experiment right now, although we may have tried a little bit, we don't think we have really the power to do any of these off-resonant excitations. So we really have to go level by level to step up the ladder. Okay, so as we continue to push the measurement of these systems out to larger and larger values to continue verifying that the Hamiltonians we think we're applying are the ones that we're applying, this sort of scalability is going to be crucial as we move to the realm of 30 plus spins where classical computation can no longer really check that the results that we're getting are accurate. And so to that end, we're starting to focus our efforts on scaling up our system. We've done quantum simulations with 16 ions where in an antiferromagnetic simulation you can see the rise of these staggered correlations start to come out. And we've also done ferromagnetic simulations where you can see this bifurcation, the difference between starting in the paramagnetic phase and the ferromagnetic phase where we're either all spin up or all spin down. We've even pushed on a little bit to 18-ion quantum simulations, although the asymmetry between the all-up and the all-down state needs a little work, so that's something we're still investigating. And as well, if we want to start going to the 30-plus spins where classical computations become intractable, it's very likely that we're going to have to go into a cryogenic-type apparatus where everything here is at 4 Kelvin. We can benefit from the excellent cryopumping that you get on the walls and really reduce our background gas pressure so that collisions, which are the thing that's limiting the large chains now, those collisions will no longer be an issue for us. Okay, and just the last little bit here, I wanted to say with some of our future physics that we're looking to do, we're really getting into this regime of many-body dynamics. Crossing phase transitions not in equilibrium, looking at critical exponents and figuring out perhaps some universal scaling behavior that we might have in our system is really a direction we'd like to go in these ion chains, as well as a number of proposals that we really think we can do in our system, where we talk to an individual ion, we use some optical pumping or dissipative beam, and then we watch as the correlations either propagate throughout the chain or how the rest of the chain tries to thermalize with such a defect. And one thing that I also thought that I put up, which is very preliminary, we're also very interested in studies of Lieb-Robinson-type bounds in long-range interaction systems, where in an experiment like this, we can initialize all of our spins to point along a z direction. We can turn on our Ising Hamiltonian, that's a global quench, and then we can measure all of the spin correlations as we move along z as a function of time. And again, this is very preliminary data, but what we find is, in fact, this sort of light cone type behavior where the correlations don't really exist at short times outside of this effective light cone. And so that's something that we can continue to study in our system, especially with the tunable range interaction, perhaps see if this is always straight or if this bends over or if there are other types of bounds that we can measure experimentally in these sorts of systems. Okay, so in conclusion, I've talked about a number of our recent results. We've used controlled quantum fluctuations to drive classical phase transitions and make a whole bunch of states that would otherwise be classically inaccessible and map out what these phase transition locations would be. We've also performed a spectroscopy of our engineered Hamiltonian, and we've really started to verify that the Hamiltonian that the ion C is the one we think we're giving it. Currently, we're looking at larger numbers of ions, and we're really pushing into these dynamical type regimes with these experiments. And finally, I'd just like to thank everybody who's worked on the project in red here, especially Crystal Senko, who's in the audience. Without all of their help, this work wouldn't have been possible. Okay, thank you.
Nice work. I have a question about your scalability claim. You say that it's scalable because you only need, you get n eigenvalues or frequencies from one frequency scan, but the JIJs go as a power law of the distance between the two ions, whatever I time minus j to the alpha. And so it seems to me that the frequency scans then need to get exponentially slower because the eigenvalues are going to get denser and denser and closer.
Yeah, I see. I think even though they're getting closer and closer, we know kind of by the math of what state we're starting in and the state that we're going to, that we always have kind of n different frequencies that we need to search for in our parameter space. And when we take data with the camera, we get all of it for free at once. We just have to know in which bins to look. And so knowing exactly what states we're creating, we can go in directly and measure what each of those individual frequency splittings are for the states that we know about. And using that, I don't think there's any kind of crosstalk for the ion splittings getting closer and closer together, even though that is true. We will be able to resolve each one individually because we can look at each state individually.
If I didn't tell you how many ions there were and what to expect, would you still be able to do it?
I would guess not. I think this implicit here is that we know how many ions are in our trap, and we know kind of that we're trying to measure the couplings of a 40 by 40 matrix. So I think that's maybe implicit in the measurement.
Thank you.
So as a sort of related question, have you had a chance to look at what happens for Hamiltonians that are not frustration-free? By frustration-free, I mean the terms in the Hamiltonian all commute with each other.
No, we haven't, but clearly you have something in mind. And maybe we can talk about it, but we've only done it for this frustrated AFM Hamiltonian.
Okay, yeah, but it's frustrated, but it's actually frustration-free. because the terms which means that the matrix, as you say, is a 45 volt, not actually exponential. So experimentally, could you do the same probe with the transverse field on DC?
I don't see why not. I think really the key here is that we have non-commuting terms and we have the sigma y that is actually giving us this transition. And so I think the method should be kind of equally applicable to those Hamiltonians and in fact other non-ion trap systems as well. Whenever you just take this transverse field and you modulate it.
There's nothing in your way of having a DC plus oscillator.
That's right. Now we need to be a little bit careful. This kind of comes back to another technical maybe issue, which is laser power. If you oscillate, if you make large excursions and the energy level diagram is sloped rather than flat, then you can imagine that you'd be smearing out your resonance a little bit, and that could be more difficult to figure out where it is. Apart from those and the way to get around that is to have more laser power so that you can make your perturbation even smaller. But that's a technical point.
I just want to add a comment to follow up on that. Tomorrow I'm going to talk about a different way that you can do the spectroscopy as well that won't suffer from having contributions from different energy levels as you're doing the experiment.
Right. Yeah. I might also add on top of that we've been talking with Jim a bit, and I think his method might even be a better way forward when you're trying to do spectroscopy not around zero field, but maybe it's some arbitrary high field where this issue might be a problem for this method.
Okay, well, let's thank Phil again.